sometimes be difficult for them to get to someone who needs help quickly, even if they use helicopters. But the Great Northern Ambulance Service is hoping that with a jet suit like this, journeys that would usually take around 25 minutes on foot would be cut to about 90 seconds.
Yeah.
It wants to launch the world's first jet suit paramedic. Richard Browning used a jetpack he invented for a special test flight.
The jet suits, they work by using pretty much the same things that you have on a jet aircraft. Two on each arm, one on the back, and the way
Very cool, actually.
then blow so much air downwards.
Cuts out on exercise if you're hiking.
And then all the maneuverability is actually down to using your own natural human balance.
I guess you can see the jets on the ruffling the grass underneath.
Some means would be much shorter than this. And Richard says it's also safe for the person flying, even if something goes wrong. Ambulance service hope that with some changes to the design, we'll be able to get paramedics flying up the mountains by next summer.
Very cool. All right, bless you. All right, you've seen that before, so let's not dwell on that. And you've seen this before, but this is kind of the topic of our interest today. Actually, as you see, actually from last week, it's a parabola from Bernoulli, right? That's not the point here, but it is parabolic. I guess this goes on and on and on, so I'll mute it. That's kind of the topic of what we'll talk about today. We'll continue on from our conservation of mass, and in the same theme that the 6.1, which wasn't published and online, is now online and closes for extra credit on Sunday. So I didn't put it online. Someone reminded me, where is it? And so I looked for it and I couldn't find it. I found it on my account, but not on the student view. So that's now online. The review session for the next midterm is still not online. Maybe it will be after this weekend. I've told you it's 3 through 7, the chapters, and we're only on 6 now, so it's not for a couple of weeks. But for those of you wanting to prepare early, that's fine. But anyway, we don't need to deal with that. Anything else we need to deal with before we get rolling today? No? Okay. It's very conciliatory of me. No? Yeah. Hearing nothing, I will move on. All right, so, well, I made a bit of a dog's breakfast at the end of the last period solving this example. Actually, the solution was right. If you remember, we're pumping air into a tire at some velocity, some initial density, rho 0, maybe. And we had this expression, and I was trying to figure out what pressure was doing there in terms of newtons per meter squared. Of course, it's not pressure, just my bad writing. It's density, and the units do match up. They're in kilograms per kilograms. And so the bottom line for this is that if we look at pushing fluid into this, the control volume doesn't change. So this term is 0. The density of the fluid does change because you're pushing more into it and it has no outlet. So this term must be finite. And this term is also finite because you're injecting fluid in there. Then you end up with an expression that includes an integral in time. And if you get that, I suppose you would know that you're injecting at 1 kilogram per meter cubed if it's air. And you're doing it for a certain period of time. And so you'd be able to calculate what the final density was in here, rho 1. And of course, if you know rho 1, then you know from the ideal gas law that P over rho is equal to RT, which is, if it's isothermal, it's constant. So if you knew the initial pressure was atmospheric, 101 kilonewtons per meter cubed, then you'd also know that P 0 over rho 0 is equal to P1 over rho 1. So you know the final density, you know the initial density. If you know the initial pressure in your tire, if it's deflated, is atmospheric, then you can calculate the final pressure, which would be in absolute pressure. So this would be 100 kilonewtons, and this would be something larger than 100 kilonewtons, because this would increase. So I thought we might just clear that up, to clear my mistake up, so you have that. So it was, actually, the calculation was right, but my reconciling of units, I was using the wrong units. And it's actually, whoops. It's actually done here. This is the same calculation. So, all right, let's recap and talk about what we want to talk about today. I'm not sure what order to do this in. Well, let's just recap what we talked about last time. We said that we're solving for conservation of mass. If that's the case, we use Reynolds transport theorem. This extensive parameter is equal to mass. The intensive parameter B is equal to mass per unit mass, which is 1. This goes to being 1. This goes to being 1. And the change in mass within the whole system is also equal to 0. And so we end up with a relationship like this. This is velocity normal to the boundary. And you've noticed that it's replaced here with a W. So maybe I should explain exactly what that means. And so we've just looked at a little video, I guess, of Fire Department of New York. I don't know why I always draw my boats like this, but I do. Is that someone snapping their knuckles? Oh. Fire Department of New York, they have fluid coming out of the hose at some velocity, which we'll call W. We know that the boat is going at some velocity, which we'll call velocity of the control surface, VCS. And so if we add those two together, this would be VCS here. Maybe I should draw it here. This is just VCS. And so the whole idea is that if we look at those lengths, then to a static observer, the velocity would be this length here, right? So the boat's happy to go on at 1 meter a second. It's squirting out water at 10 meters a second. Then this should be the vector sum of those. And so we remember that velocity is a vector. It has not only magnitude but also direction. It could be, the boat could be going up, I guess, if for some reason, but it's not logical for this particular example. And so in the same way that we defined our previous substantial derivatives, we had to define it in terms of a specific reference frame. Either uppercase dv dt is attached to you as you're falling through the air, or if you're looking at someone falling through the air, lowercase dv dt and dv dz are the two parameters that that particle has. A velocity relative to the static as it's falling, and also if you take a picture now and you take a picture 10 minutes later, if the velocity of that particle has changed, of course, the person has gone out of the frame, but if it's water, it's still coming down at the same rate as in a free jet, then we can look at that. So we need to use reference frames and be mindful of that. And so this relates back to what we'll play around with today, is that we'll go back to the idea that we can define 3 different frames of reference for these calculations. And they're neatly given by these little silly diagrams here. And we can have a static, non-deforming reference volume. Pipe, water comes in upstream, water goes out downstream. Control surface doesn't move, and it doesn't change in size. A jet engine, where it doesn't change in size with time, but potentially it moves in the system. So it has a velocity with it. And one in which, not a balloon, in which not only does the control surface move, so this would be what we just drew, the velocity of the control surface as it zips around the room, but also the control volume, the volume of the control, well, I guess we call it the control volume. Let's call it the control volume. This also changes as well, right? The balloon gets smaller as it exhales, expels air. So if you look at the velocity on another part of the contour, then there's no reason that this velocity and this control velocity should be the same, because the balloon is shrinking, right? This could be going at 1 meter a second. This is shrinking by 0.1 meter a second. So this would be going at, this could be going at 1.1 meters a second, because it's shrinking to catch up, right? So those are the three control volume and control surfaces that we'll entertain to be able to solve a very simple problem 3 different ways and get the same answer. So that's all I want to do today. So I'll keep on talking about redefine exactly what our controls are. And I wrote these down so that I won't screw it up today. And so this Reynolds transport theorem, once we do this, it looks like this. This is accumulation, rate of mass accumulation. And it can happen, and we typically write it like this. It's a bit more easy, a bit more straightforward. And this is mass rate out minus mass rate in physical terms. We said we use the dot product of velocity, so it's normal to the boundary. So that gives us a single value as it crosses any particular boundary. Of course, we could draw a control volume. The control volume, I guess, could look like this. So this would be the volume. This is control volume. This is the velocity it's traveling at, VCS. Same as this. And of course, across this boundary of the control volume, we're squirting water out. We chose to do it normal to the boundary, so this would be a positive velocity out because it's coming out of the system, such that mass rate out is positive, mass rate in is negative. So it's important for us to know our sign convention, and perhaps we should just revisit that once again. Is that knuckles being broken? Remember that we defined a couple of different things. We defined a unit normal, which is a vector, and it's an outward normal. And we're going to define in red, a velocity. We'll call it V, or we can call it W. Let's call it W. So W here, because this is our coordinate system, X and Z. So W here is positive because it's in the positive X direction. But W dot N is also positive, right? Because what we said about the dot product of something. Dot product of something is just the component of it in the direction of the coordinate system. So this could be W. No, it's not W. Yeah, this is, let's get rid of that. This is W, and this is W cosine theta. If this is theta, this is the dot product for a single component. It's just the component in the direction that you want to get it. And that's all this is doing. Likewise, in this, if this was the velocity in here, then this would also be positive, but W dot N would be negative W because it's into this. So this is the direction of the normal. The W is in the opposite direction, 180 degrees. Cosine 180 degrees is -1. So the product of these is equal to this. So just need to be mindful of that. The other terms that we have, and we did this last time, so this, we can write this expression if we take the derivative to account for both a change in volume and a change in density. So we did the example with a tire. The volume of the tire doesn't change, but the density of the fluid has to fit in more fluid as it goes in. You could fill up a tank, and of course the tank level is rising, the volume is rising, but the density of the fluid isn't. So you can look at those two conditions by just differentiating this. So this is rate of change with time of volume times density, plus rate of change with time of density times volume, plus sum of density times velocity times area. This has to be the normal to the boundary velocity equals 0. So we know the sign convention for this. This is always positive. This is always positive out of the system. But we also have the sign convention for this. So the sign convention for this is that if within this container here, with time, the density or the volume increase, then this is positive. And if it's decreasing, then it would be negative by sign convention, right? So increase in volume with time at a constant density, or an increase in density for constant volume. In the example we just did, the sign convention for these is also is positive for that. So that's what we need to deal with. So that we're nearly ready to get going then. And so we need to be aware of this. This is the equation we'll typically use. If it's steady state, then both of these terms here will drop out, and it's just the sum of these that equals 0. And what we're going to do is we're going to try and solve the problem for how long does it take to fill a bucket. So you have a 10-liter bucket, you're putting water in at 1 liter a second, it takes 10 seconds to fill it. You know that. And so I guess this is the sign convention for this. Yeah, I guess that's this. So this is that. So how long to fill a bucket? And so if we want to calculate, have the volume of the bucket, and we fill it with something, a volume per unit time. So 1 liter per second times 10 seconds equals 10 liters. That's all you do. You do it intuitively in your mind. So this is dV dt. This is just shorthand for change in volume with time. Is superscripted dot. Again, volumes and velocities, that's the reason for drawing a bar through them. And so if we have this, what we could do if you want to do that calculation, which you just did, just rearrange it in terms of time. How long does it take to fill the bucket? The volume divided by the volume rate. That's exactly what you do. We should do it in terms of mass, multiply it by density. This volume becomes meters cubed times kilograms per meters cubed. So this is kilograms divided by kilograms per second. So it all works out. And so this would actually be a mass divided by a mass rate. And so that's useful to do because that's exactly what this expression is. This is a mass rate in or out. These are mass rates of accumulation, and they're all in the same units. So if you want to solve this problem, let's start with it partly filled. And I'll go back to the little video again. Well, not again, because you haven't looked at it. If you're at this level and you want to fill it up a height h, then mass rate is equal to mass divided by time. Time is equal to mass over mass rate, which is what we have here. Divide both sides through by density and put in the volume. The volume is going to be the cross-sectional area of here, which is A2. The height that it needs to fill, so this term on the top is just volume, and the term on the bottom is just the velocity of water in multiplied by the cross-sectional area of this thing here, A1. So the velocity, so this is just equal to velocity rate in divided by volume. Sorry, volume rate in divided by volume. That's what you do. So that's really all we're trying to do. So let's try and make our lives complicated by trying to skin this cat in 3 different ways. And let's look at this first. So this is my downstairs where I used to make beer. Don't make beer anymore, but that's what it's set up for. Beer glass, of course. And so, not sure it's annotated. It doesn't need to be full screen. So what if we look at this? What do we know about the fluid mechanics of this? So we start filling it. We have a jet coming in. Well, we see something, right? It's a bit murky, but where it comes out, we know from free jets that because the velocity here is going to be less than the velocity here, just acceleration due to gravity, then if this is a streamline that encases this, then from continuity, this cross-sectional area here has to be larger than the cross-sectional area here, and it is. But what we want to use this for is to be able to draw some control volumes on this to be able to solve this particular problem. And so if we wanted to do that, I guess I did it, I think on here. I solved it here the other day, so a bit too big, but never mind. So I got this. So if we could solve it, let's actually go back to the 3 different cases. Not doing a very good advertisement for continuity here myself. So these are the 3 different cases. So static non-deforming would be our pipe. So it's a control volume that something comes through from upstream and goes downstream. The moving but non-deforming, if I draw it in the same sense, would be the jet engine with poetic license. So this moves at some velocity VCS. So the velocity of the control surface is equal to the velocity of the control volume because this volume is rigid. So if you look at the velocity here, it's the same as the velocity here, and it's the same as the velocity everywhere on the contour. So the velocity of the control surface is equal to the velocity of the control volume. And so finally, the one that has the balloon in it, as we said before, the velocity of the control surface here isn't necessarily the same as the velocity of the control surface here because the balloon might be shrinking. And so actually the velocity of the control surface has to be actually the velocity of the control surface because it's not constant around it. Perhaps a small point, but nonetheless important. What about the change in volume with time that we use up in this expression here? We use the change in volume with time here. Well, for non-deforming, clearly this volume isn't changing with time. For this one, because it's not deforming, it's translating for sure, but the volume inside this control volume isn't changing with time. So that is 0 here. So these are that. And the only one that is changing with time is the deforming one. So those are the 3 classifications: static non-deforming, moving non-deforming, and moving deforming, getting progressively more complex. And they're given by these conditions. So what we'll do is we'll try and use this expression here to rationalize those 3 different solutions for solving exactly this problem here. And I'll draw on here what we're going to try and do for that. So what would they look like? I suppose that the easiest one is static non-deforming. So you can imagine that at the bottom of this, can you see that? I guess I could make it bigger. It's this one, I guess. So I'm going to draw 3 different cases to represent this. So this is a control surface that encompasses a control volume. And what we have is we have some velocity of fluid in here and some velocity of fluid out of here. It's steady state, so actually you'd be able to calculate that if this was area 1 and if this was area 2, you could think of this as a big streamline coming down. Actually, you could think of it like this, I suppose, right? Even though it's a bit like this, right? This would be V1A1, and this would be V2A2. Just from continuity, you would write intuitively V1, I hope, A1 equals V2 A2. And so if you know what V1 is, you could write V2 as being equal to the velocity you know times A1 over A2. That's it. That's kind of what it would be, right? So that's the example of a static, non-deforming control volume. The green contour is the control surface. It's not moving. The volume is the volume inside that surface, which we call V. And we'll go back to these and do them in excruciating detail, actually. But this is the basic idea of that. So I'm going to erase that. I guess I don't need to erase the whole thing. I can erase this. Right? God. Perhaps I can't erase it. All right. So I guess that's the problem with that. So I need to use this. If I don't, I think it just gets rid of the stuff I don't want. Close enough. All right. Second one. So the first one was our static non-deforming. What was the next one? Next one was a jet engine. So that's moving non-deforming. So what that would be? I think that would be something like this. I'm not going to draw it to the bottom of the glass. So now this is able to move up at some velocity. It's not going to change in size as it moves up. So certainly over part of this length, you would have fluid going in at some velocity. If we chose to anchor this control surface velocity to the velocity at which the level is rising, then we'd also have to account for another fact that out of the bottom of this would also be flowing some fluid, right? Because you could imagine that if this streamline that comes in does an about face and just goes up to the surface where it stops, it doesn't get down here. This is all stagnant water. So if this whole control volume, which isn't changing in volume, is translating upwards, then it's accepting water across this boundary. This is following the free surface because we're just going to say that it goes up at the same velocity as it's rising. So there's nothing that comes across this boundary. And then the stagnant water, which is present here, just gets swept across by the bottom of the control surface. And we'd have to account for this as a velocity W coming out of the bottom, if this was Wn. Okay? Just conceptual ideas. We'll go through them again, as I say, in excruciating detail. Okay? And so I will also attempt to get rid of this if I can. And you get, obviously in these, you get exactly the same result, which is, you should do, right? It's the same physical system. So now, 3, this was 1, 2, and 3. So moving and deforming the balloon. And what would that be? That would be this. Let's take the whole thing. And so now water would be coming in here. This surface would be going up at the velocity of the control surface. But this velocity here would be 0 because we're fixing it. So got a control volume anchored at the bottom, velocity is 0. It's stretching upwards at the same rate as the upper surface is rising, so it's getting bigger. So certainly the volume of this is changing. This would be a velocity of water coming in. The velocity of water going out here would be 0, right, because it's anchored. Nothing going across it. And also the velocity of whatever's coming out of here, which I'll draw in blue, this also has to be 0 as well, right? W3 equals 0. Can you see that? Yeah, not too bad. So those are the 3 cases. And so obviously what we'd like to calculate is how long does it take to fill the glass? And that would be the simple calculation. And it's no different from the calculation we just did, just taking a volume divided by a volume rate gives a time. And so we'll attempt to do that. So those are the 3 conditions. Let's try and evaluate those individually. So I wrote this out. These are actually the things on my notes, but I won't do that. This is what we just did. We can make our life a lot easier than instead of filling it from the top, where we have to account for stuff coming across the control volume that's moving upwards, we can fill it from the bottom. So we're filling it from the bottom in this particular case. We start off with a given height. We have an extra height to fill within the cylinder. It's not a tapered glass anymore. It has a cross-sectional area A2. The jet coming in has a cross-sectional area A1. And the surface would be going up at some velocity, which we can call V2. So the simplest way to do that is this. The first one is a static, non-deforming control volume. So this is, I guess it's a blunt instrument now. Don't want it so blunt. Oh, I thought it returned back to the thing again. So this is, our 1 is static, non-deforming. So it's the pipe that water is flowing through, in other words. So we can define our expression, density times rate of change of volume, plus volume times rate of change of density, plus mass rate out minus mass rate in is this. The static, non-deforming, so this by definition has to be 0. The density is not changing. It's water, it's not changing. So it stays at the density of water because it's not under pressure. And so we're just left that the sum of the mass rates in minus mass rates out minus mass rates in equals 0. So there are only two places where that can occur. There's a mass rate in to the bottom, and there's a mass rate out of the top. This green line is not going anywhere. It's static, and it's not getting bigger. And so if these mass rates added together, if we write them out, it's equal to the density times the velocity. The velocity 1 is in, therefore negative, right? It's normal to the outward normal. It's in the opposite direction of the outward normal. So this is minus V1 times density times A1. The fluid coming out the top is coming out across this boundary at some velocity V2, which we don't know. It's coming out, so it's in the same direction as the unit normal, right? The unit normal, wrong color, choose a different color, perhaps not to confuse. We've used a unit normal being this before, right? It's in the same direction as this, so this is the case. And actually, if you look at this, this is just our, we drew it before. This is our streamline continuity. This is V1, A1 rho. This is, I'll write it in the same order, rho A2, V2. We never took account of the in and outs before, but we are doing this. This would be a positive value, and this would be a negative value because it's going in, and we equate them equal to each other. It's just a different sign convention, but it's the same thing. And so if we do this, we can write this expression in terms of V2. These equate to each other, so this just becomes V2 is equal to V1 A1 over V2, just from this expression here. And if we know what V1 is, we know what the cross-sectional areas are, we can always get V2. And if we know that the height it has to go in a given time is equal to, so we could also write this as V2 equals H over T. Let's write it, actually let's write it the way we had it before. What do we have? T is equal to volume divided by volume rate. So for this expression, volume is equal to H times A2. Volume rate is equal to V2 times, sorry, V1 A1. Is that right? Velocity times, yeah, that's the volume rate. And so that's just this expression here. So it's just saying that it goes up at this velocity V2, it has to travel a distance h, and so if it's traveling a distance h at the velocity, you can calculate the time it takes to go between those two locations. So that's the first one. Okay. So if we want to make our lives a bit more challenging, the second one, I guess, would be moving and non-deforming. So the jet engine, if you like. So this is what we said. So it's not getting bigger control volume. So what we would do is we'd have a control volume that could be anywhere within the fluid. we can prescribe any velocity we want that it would travel with. And it's not changing its volume, but certainly these surfaces are moving, and they must be moving in unison at the same velocity because it's not deforming. So we have to use this concept of our relative velocities. So if we have water squirting out at 10 meters a second, the boat moving at 1, then relative to a static observer, it's moved. This bead of water that's coming out at the front of this is moving at 11 meters a second. And so for a static observer, it's the velocity of the control surface plus the flow rate across the control surface. We can rearrange that just by moving CS onto the other side. We can then come back to our expression. So if we look at what these would be, let's not take these as given, but I guess I'll just replace those. What is our system doing? The volume of the control volume isn't changing. So by definition, this has to be 0. The density of the fluid, because it's atmospheric, it's not getting compressed. And so this has to be also 0. And we're left with this expression now, which we've written in terms of the relative to the boundary velocities. It's the same as if you're traveling with a bucket and you're spilling water out of the bucket at 1 kilogram per second, it's that amount that's coming out of the bucket. It doesn't care about any other reference frame. It's just what's coming out of the contour of the bucket. And so we can use this value to define that particular magnitude. And so for this behavior, it's actually, again, it's no different if you think about it from our streamline. Perhaps it's more, bless you. You know, water's coming in here and it's going out here. So this could be the same as W1, W2. We've just changed the name of it, times A2 and A1. Actually, it's no different from that, right? And so for this, W1, A1 density is equal to density W2, A2, from the way we used to do it. But we write it a different way just because of our sign convention. So if we take care of this sign convention, V1 is into this. The normal to the boundary is in this direction here. And so this is minus term here. V1, I should have said W1. W2 relative to the outward normal. This is the outward normal. This is in the same direction. So this is positive, and it equals 0. Subtract one side from the other, you get this exact expression here. And then what do we do? Easiest thing to do is let's attach this top of this control volume to the rising tide as it rises up the glass. So if we make the velocity of the control volume, control surface, equal to the velocity of the fluid, V2, then this is the case. And if V2 relative to the static observer is the same as the rise of the control volume, the water's rising at V2, we attach the control surface to it, so it's rising at the same velocity. These two velocities are the same, so W must be 0. And so actually we can't solve it this way because we don't have anything to be able to solve. So actually what we have to rely on is the fact that since this surface is going up at V2, this surface here has to be also migrating up at V2, and therefore we can do the conservation equation on this volume here. This surface is going up at V2, which is this, times A2. This is being fed by V1, A1. So actually we have to revert exactly to this behavior to get the velocity of V2 of this rising surface as being equal to the ratio of the two areas. Exactly what you'd get just if you rearrange this, right? This would be accepting the velocities. And so if you do this, you again get the time that it takes to fill is equal to the length traveled, which is the height the surface rises, divided by the velocity at which the top surface is going up. This is just the time taken to travel a distance h. So that's it. So you get exactly the same result as you should do. And then finally, I guess it's the balloon, so I guess I won't write it out again, but I will draw the whoopee cushion as it flies through the air. You know that the rate of change of the control volume is not equal to 0 by definition. And we know that the control surface is traveling at some volume, so that's also not equal to 0. It's equal to the control surface. So if we take our Reynolds transport theorem, continuity, which has rate of mass accumulation on the left, mass rate out minus mass rate in on the right, and look at those terms. This term is not equal to 0 anymore, right? The volume of the balloon is changing. So we're going to draw a control surface, just as we did for the third of the cases in the example in the video. We're going to anchor the control surface so the bottom is moving at 0 velocity. So I guess this is VCS equals 0. But the velocity of the control surface at the top is VCS, which is not equal to 0, right? It's expanding. And so the rate of change of the volume is not equal to 0, so we have to keep that there. The density of the fluid, because it's under atmospheric pressure, isn't changing, and so we can get rid of this. And we have some amounts of fluid going in and some amounts of fluid going out. We make our life the easiest if we take this top surface and anchor it to the rising tide, to the rate at which the fluid is going up. So in other words, if it's anchored to the rate at which fluid is rising, there's no fluid going across that boundary, because you could think of it just as a float that's rising in a cistern with the rising of the water level. So this has to be, W2 has to be 0. If we are anchoring the bottom to the bottom of this here, then the velocity across that boundary has to be whatever it's coming in at. It's not moving, so it's equal to number 1, velocity 1. It only comes in on the portion of the boundary which is open, and so the amount coming in would be equal to W1 times the area over which it comes. So this is finite, the volume's changing, the density's not changing, and we only have one term coming across. The density, the velocity times the area. This isn't moving, and so W and V are the same thing, right? It's coming in, so the normal to the boundary would be in this direction here. So this velocity in is negative, hence this term here, and it's also equal to V1 because it's not moving. We've anchored this as a float to the surface that's rising, so there's no fluid crossing this upper surface, so it's equal to 0. And so as a result of that, we've got that the density times the rate of change in volume has to equal the mass rate of fluid that's supplied in the bottom. Take it to the other side so they equal each other. We can delete the densities on each side, and we end up with rate of change of velocity is equal to the velocity that this control surface at the top is traveling upwards times its area. The volume that it has to fill is going to be the cross-sectional area here times the height it needs to travel. This is h. And so if we did do exactly what we did before, the time it takes to fill is equal to the volume it has to fill divided by the volume rate at which supply occurs, time. the volume is equal to A2H, which is the top, and the volume rate is equal to velocity coming in times the cross-sectional area. And so all the answers we get are exactly the same as the most simple case we took, and that is that if we want to calculate the time to fill something from this equation here, then it's just equal to the mass of the container when it's filled divided by its mass rate. If we divide mass by density, then they just become a volume filled divided by a volume rate. And that's all it is. And so this happens to be just how you intuitively do it. Bucket, 10 liters, 10 liters, 1 liter a second, therefore it takes 10 seconds to fill. You just do that intuitively. But all we're doing for these others is exactly the same thing, but just doing it with being mindful of a formalism with a control volume. Where the control volume is static, then you have water coming out of the top and coming into the bottom. They have to balance each other, just like a streamline. It's just that when we write our conservation of mass equation, we do it with a specific sign convention where flow into the system is negative and flow out of the system is positive. But it's just exactly the same as this. Here we looked at flow into the system as positive and flow out of the system as positive and equated them to each other. So we can write them as rho V1 A1 minus rho V2 A2 equals 0. If we take account for the fact that these velocities are out or in, or if we just look at them as being equivalent to each other, then when we talked about Bernoulli, we just wrote them as rho V1 A1 equals rho V2 A2. Missing a sign. So it ends up being the same if you subtract them from each other, right? And subtract them, they're actually equivalent to each other. And so we do that here. When this is not deforming, mass rate in equals mass rate out. There is no change in volume of the control surface. And so this is just a streamline. If we do it here, we get mass rate out and mass rate in. If this is moving up at the same height, same rate as the rising tide, then there can be no mass rate across this surface. And if this isn't changing volume, then there can't be anything coming in the bottom either. Right? That just is intuitively the case. So actually we can't solve this case for that other than writing with the control volume being the volume below it, which is expanding at the rate of this lower boundary going upwards. And so that's what we did here to be able to solve it. We just took a control volume. If this is going up with the top of the surface, then this has to be migrating up at the same rate as the top of the surface as well. And so really we can draw a control volume which is just getting bigger as we flow water in here and nothing comes out across this boundary. And it's just the same as the simple solution we got in the first case. And then finally, to do it as a deforming case, then we can have flow across here, but the flow across this part here is only equal to the amount that comes in. If we attach this to the rising boundary, so there's nothing flowing across it, then W2 is equal to 0. If W2 is equal to 0, then V1 A1 times the density has to equal to the density times the rate of change of volume of this control surface. That's really all we're saying. And so if we know what the velocity in is, we know the cross-sectional area, and we know the densities, we can calculate the volume rate. If we know the volume rate and how much we have to fill, we can calculate the time it takes to fill. So, as I say, 3 very complicated ways of solving the problem, but that gets us there. The reason that we've spent some time on this is it's not so important for solving problems like this to do it this way. But when we look at conservation of momentum, one of the things we might want to do is take a fire hose and point it at someone's chest to push them over, or point it at a vane on a water wheel to be able to spin that Pelton wheel around. So we'd like to take the static velocity of that hose and make it do some work in spinning a wheel, in which case we have to look at these frames of reference and different